Okay guys, welcome back to another video. We are going to section 1.2 of chapter 1 of number theory, and the topic is the principle of mathematical induction. So what is mathematical induction? It is a method of proof that validates a general result in mathematics involving natural numbers or positive integer. You may have a statement involving n, where n is in a set of natural number. And today we want to prove this theorem by using the value ordering principle. And this theorem is the principle of mathematical induction. So let's take a look. So let S be a subset of a set of natural number. And then S, the set S is a set of natural number if and only if the first condition is true, which is 1 is in set S, and B, if n is in set S, n plus 1 is in set S. Okay, namely that if we have subset of natural number and S is a set of natural number if and only if 1 is in set S, and if n is in S, then n plus 1 is in set S. Okay, or vice versa, if 1 is in set S and if n is in set S and then n plus 1 is in set S, it can be concluded that S is a set of natural number. Okay, let's prove it. To prove this, we have to use value ordering principle. Remember what it is? A subset of natural number always has a minimum elements. Okay, let's get started. Let's prove this one. So I gotta assume that we have subset. Assume that S is a subset of set of natural number, and we have if and only if. Once we have if and only if, we imply from the left to the right, right? The left imply the right, or the right implies the left. Okay, so I want to start from the left imply the right. Okay, so we have to assume that S equal to set of natural numbers. So assume that S is a set of natural number, and we want to show that A and B are true. Okay, show that A and B are both true. Okay, I think it's pretty obvious. It's quite obvious. Why? Because set S is a set of natural number already. So we know that 1 is in a set of natural number. Okay, so since S is in set of natural number and 1 is already in the set of natural number, this means that 1 will be in S. Okay, so A is true, right? A is true. Okay, because 1 is in set S already. Now let's prove B. To prove B, we have to assume that n is in S and then show that n plus 1 is in S. So assume that n is in set S, okay? But since we know that S is a set of natural number, so S must be in the set of natural number, okay? So n, not S, n is in the set of natural number. And 1 is already in the set of natural number. We use trigonometry law, okay? So by trichotomy law, the second law, we can have n plus 1 in the set of natural number. And the set of natural number is set S. Okay, so n plus 1 is in set S, and hence B is true. Okay, hence B is true. So we prove that A and B are both true. Okay, let's go to another one. Let's go to right imply left. Okay, so let's assume that we have to assume that A and B are both true. Okay, assume that A and B are both true, meaning 1 is in S, and when S is in set S, n plus 1 is in set S. Okay, and we want to show that S equal to n. Okay, we try to show that set S equal to the set of natural number. How come can we do it? How? So we already have S is a subset of natural number already. The next thing we gotta do is to show that set of natural number is a subset of S. I don't want to do it directly, okay? Because when I let X to be a set of natural number, then I don't know what to do. Alright, so let's assume I want to use a proof by contradiction. So I gotta suppose that set of S is not a set of natural number. Okay, so according to the assumption, S is a subset of a set of natural number, and S is not equal to set N. So what do we have? And S is not equal to set N. Okay, this means that set S is smaller than set N, right? The picture might look like this: set N and a set S and a set of natural number is pretty much smaller. Okay, it's smaller. So this means that what does it mean? Okay, this means that when you exclude all the element in set S, exclude all of it, you have element in set N, right? Okay, so it's not empty set. It's not empty set. And set S excluding set N excluding S, or set N how do we say it? Different S, okay? Set N different S, exclude all this. We have many elements in set S. This means that the set of natural number different set S is a subset of a set of natural number. Okay, good. Now what can we do? What can we do? It satisfies well ordering principle. Okay? Because we have subset of natural number, and this subset of natural number is not empty. So we can use well ordering principle. So the well ordering principle, what does it imply? Implies that this set will has a minimum element. Okay, let's say that this minimum element is x. Okay, when x is a minimum element, what does it mean? It means that it must be less than or equal to all element in subset of n. In this case is the set of natural number excluding set S. Oh, I have to write A in this set. Okay, so for this statement, you can say that A x is now a minimum. You can call it the minimum element, okay, or the least element. The how do we say it? The smallest elements, okay, is the smallest element in a set of natural number excluding set S. Yeah. Okay. So right now x is in a set of natural number excluding set S. What does it mean? It means that x must be a natural number and x is not in set S. Okay? It's not. Right? It's not. It must be like this. It's not. Okay. It's certainly not, because x must be somewhere here. Okay? If element is in set S and we exclude S, okay, that element disappear with S. In this case, x is in a set of natural number but is not in set S. Okay, so what can we do next? X is in a set of natural number. My question is, can we find the element that is less than x? Can we do that? Okay, so let's pick this element. I want to observe x minus 1. It's pretty obvious that x is less than x. X minus 1 is less than x. And okay, and x is in a set of natural number which is the smallest element in a set of natural number. What does it mean by this? If you look at x minus 1, that is less than x, and x is the smallest one. This means that x minus 1 is not in this set. Okay? It's not, because it's less than x. But x is the smallest. So x minus 1 is not in this set, a set of natural number different set S. It's not in here. Okay, how do we go? Let's use assumptions here. So A, we know that A is true and B is true. Let's use A. So since A is true, okay, since A is true, what is that? 1 is in set S. Okay, great. 1 is in set S. Okay. but 1 is included in a set of natural number. This is a mathematical fact. In fact, 1 is in a set of natural number. What happened? 1 is in S and 1 is in a set of natural number. This means that S and N has 1 as a common element. So if we exclude N, if we exclude S, 1 will be disappear from this set. So this implies that one is not in a set of natural number excluding set S. Okay, great. So what can we do next? Let's go back to X is being in this set. Okay, so since X is in a set of natural number excluding S and 1 is not in here, so X is the minimum, okay, right here, or is the maximum element in this set, but 1 is not in here. So this implies that X must be greater than 1. Okay, X must be greater than 1. So what's happened is X minus 1 is greater than 0. So X minus 1 must be a positive integer. Okay, X minus 1 must be a positive integer. And then X minus 1 is not in this set. So what does it mean by this? When X minus 1 is not in the set of natural number excluding S, okay, what happened next? So let me copy this one here, this figure, and write it down here. So X minus 1 is in this set, right? But X minus 1 is in a set of natural number excluding S. I think it's going to imply that X minus 1 is a common element of S and a set of natural number. So let's take a look. So we gotta have, so when X is not in set S different S, this means that X minus 1 is not in, is in this set and complement. Okay, and it turns out to be a set of natural number intersect set of S, complement, and complement outside here. So we have a set of natural number complement union set S. Okay, so right now X minus 1 is included in a set of natural number complement union set S. So this means that X minus 1 must be in a set of natural number complement, or X minus 1 in set S. So we gotta have X minus 1 in a set of natural number, okay, or X minus 1 in set S. Okay, oh, it's not, sorry, it's not here. So X minus 1 is not in a set of natural number. So from this right here, this implies that X minus 1 is in set S. Okay, gotta say hence X minus 1 is in set S. And since X minus 1 is a positive integer and X minus 1 is in set S, so what does it mean by this? So we know that S is a subset of natural number and x minus 1 is a positive integer, and x minus 1 is in set S. So what does it imply? It implies that x minus 1 is in a set of S intersect a set of natural number. And since S is a subset of a set of natural number and we have this intersection becomes just set S. This means that x minus 1 is in set S. Okay. So, what can we do? We have 1 in set S right here, and x minus 1 in set S right here. I want to use B. Okay, I want to use B. So let's go. Okay, let's go. So since B, what does it say? B, because B is true, is up here. Okay, if you have an element in set S and then you add it by 1, it will be in set S. Okay, so now B is true and we have x minus 1 in set S. So x minus 1 is in set S right here. So we gotta have x, which is x minus 1 plus 1, and x minus 1 plus 1 is in set S according to B. So right now x is in set S, but did you remember here x is in a set of natural number but it's not in set S, but right here we have x is in set S. So right now we have a contradiction, okay, which is a contradiction, okay, to x not being in set S. So therefore what we have supposed is false. Okay, this is false, and therefore S must be a set of natural number. So we have proved the principle of mathematical induction already. Okay, so that's it for today. Okay, and go back to another video.